Okay, since the last time I have updated these elevations for the final grade straights of my profile. I intentionally left these areas blank because there will be a curve here and also there is going to be another curve around that area, so these have to be updated anyway. So the profile is more or less ready. Now the next step is to calculate the length of a vertical curve. In your case you will have only one curve, but in my case I will show you both a sag type curve and a summit crest type curve as well. That's why I have two curves here. So I'm going to calculate two different lengths. Okay, let me go to this lecture notes. So let's go back to the beginning. Yes, vertical curve calculations. There are two different types of curves as we discussed in class: crest or summit, sag or valley type curves. In my project, this is a snapshot of my project that I have been developing currently with you. I have already finalized the grades of each straight. So I have 3 straights. You will have only 2 straights. I have 3 straights: 2.1% slope, 5.07% slope, and 2.98% slope. I will have a sag type vertical curve here, and also I have a crest type, summit type vertical curve around this area. Okay, and vertical points here, vertical point of intersections are here and here as well. Starting from the first one, sag type vertical curve. The grade difference between this straight and that straight is called capital A. It may also be called capital G in some books. In our lectures you are familiarized with capital A actually. So A is 2.1% minus 5.07%, that is 297, the algebraic difference. This has got to be an absolute value. Okay, if it turns out to be a minus value, you take the absolute value of it. Similarly, my crest curve has got this A, 5.07 minus 2.98. 2.09 is the algebraic difference, absolute value. You may refer to highway engineering books for further discussion about how to calculate this A value. Okay, I just pass now. Right, for sag type vertical curves, stopping sight distance at night is more critical than any other criteria, like passing criteria, for example, because even at night in sag type vertical curves you see the headlights of the oncoming traffic, the opposite vehicles in the opposite direction, so therefore seeing them is not a problem. But stopping the vehicle in order not to hit an object at night is a problem, because it's the sight distance is limited by your headlights. That's why we have to calculate, we have to check this first. The stopping sight distance is this formula that we have been using this for in many different places. Putting the values from my project, TR is going to be 2 seconds. Sorry, yes, TR is going to be 2 seconds. The design speed is 60, and 3.4 is given in AASHTO standards. divided by the gravitational pull minus the worst case scenario is 0.05, which is my 5% slope. Remember this. So in a sag type vertical curve, okay, this slope, this straight has a higher slope, therefore vehicles coming from the right going to the left will experience the worst case scenario. We talked about this in class last week, so that's why I'm going to use this slope as as here, negative. The result is 81.2, but according to AASHTO recommendations for design speed of 60, we take the stopping sight distance as 85 meters. There's no problem. It's on the more conservative side anyway. So for a sag type vertical curve, there may be two possibilities, whether S is smaller than L or S is bigger than L. For S smaller than L, use this formula. A to remind 2.97. 2.97 times 85, we've just calculated, squared, divide by 120 plus 3.5 times 85. That gives me 51 meters. Is 51 meter indeed bigger than S, 85? No. So therefore, it's no use. In the second situation, 2 times 85 minus 120 plus 3.5 times 85 divided by 297, 29.4. Is 29.4 smaller than 85? Yes. So my length could be 29.4 meters, 30 meters. It could be, but I have to do further checks. So my sag curve, the length of my sag type curve could be 29 meters, but we have to do further checks. Comfort. Okay, for sight distance 29 meters may be enough, but for comfort reasons we have this formula again from AASHTO, American. For appearance we have this formula, and also we have a maximum value for surface water drainage purposes. Okay, let's check all of these. A times V squared divided by 395, 27 meters. 30 times A, 89 meters. And maximum 151 meters. So that means I can't use 27, I can't use 29 from the previous page because there is 89 here, minimum. So my curve has to be within 89 and 151, somewhere in between. It's up to you. You can choose, if your results are like that, for example, you can choose any value between 89 and 151. I decided to choose 150 for some other reasons, for demonstration purposes reasons in my project, okay? But it's totally up to you. You can choose between the maximum of these minimums and the surface water maximum, okay? 150. Now my second curve, that was a summit type curve, to remember, my A was 2.1 or 2.09 actually. So we're going to calculate again stopping sight distance. These are the figures, and this is the biggest slope, the mid straight, so therefore I produce the same result, 81, but I take 85 again, 85 meters for 60 kilometers an hour design speed. For S smaller than L, use this formula, and that will produce 23 meters. Is 23 meters bigger than 85? No, reject. For S is bigger than L, use this formula and produce a minus value, so therefore we can't use it. Hence we can take 80 meters again from Ashto.